Hey everyone. So in this video, I like to talk about the graphs of sine and cosine. So graphs provide us with a great way of looking at a lot of information about a function all at once. And so graphs will be really helpful for us in understanding the behavior and when it comes to analyzing the behavior of our sine and cosine function, as well as the other trigonometric functions. So let's start by graphing the sine function. F of theta is equal to sine of theta. So I've got a table partially filled out here with some inputs I'd like to evaluate for our sine function. I've also got a picture of the unit circle on the right side. So that is a graph, but it's not the graph of the sine function. The unit circle is something we use to evaluate to help us make sense of evaluating, making sense of the outputs of the sine function, but it's not actually the graph of the sine function. So when it comes to graphing the sine function, we're going to need to make sense of the input values and the output values of our function. And the input values are going to correspond to this horizontal axis here. So here I'm going to label that horizontal axis theta. So from left to right, we're going to be looking at larger and larger input values to our sine function. And then the vertical axis, well, that's going to be the outputs of our function. Here I'm just going to write that as f of theta. So let's go ahead and just start plugging in some points, some values into our sine function. So when we plug in 0 into our sine function, when theta is equal to 0, we're looking at an angle of 0 on our unit circle. And we're asking us what the y value of this point on the unit circle is, right? Sine gives us y values of the points on the unit circle. So at an angle of 0, we get the y value of 0, right? We're at the point 1, 0 on the unit circle, and the y value of that point is 0. And so on the graph of our sine function, we've got an input value of 0, our angle, and we've got an output value of 0, the y value on the unit circle. So this is the point 0, 0. That's going to appear on the graph of our function f of theta is equal to sine of theta. And so here, I don't have pi over 6 labeled. Maybe I'll put it in now. So pi over 6, here's pi over 6, here's pi over 4, and here's pi over 3. So let's look at the output values corresponding to these angles. So pi over 6, that's a 30, 60, 90 triangle on the unit circle. And sine of pi over 6 is going to give us the y coordinate of this point on the unit circle. This is going to be the short side length of this 30, 60, 90 triangle. It's going to be 1/2. And so 1/2, that looks like it's about here on this coordinate plane. So that's going to be the point on the graph of f of theta is equal to sine of theta. It's pi over 6, 1/2. So next, let's look at an angle of pi over 4. So pi over 4 corresponds to a 45, 45, 90 triangle. And here the y coordinate on this angle is going to be the square root of 2 over 2. And so that's what sine of pi over 4 is going to be. And so the square root of 2 is roughly 1.4. So cutting that in half is roughly 0.7. And so I think a reasonable place to plot this point will be about here. Okay, so at pi over 4, we've got an output of roughly 0.7. So next, we've got pi over 3. That's an angle of 60 degrees. So we've got another 30, 60, 90 triangle, but now we're looking at the long leg length corresponding to the y coordinate at this point on the unit circle. And so that's the square root of 3 over 2. And the square root of 3 is roughly 1.73. And so cutting that in half is a little bit more than 0.85. So here this is going to give us y coordinate, or an output value of roughly 0.85. I think that's a reasonable place to plot it. And then when we look at an angle of pi over 2, well, that's this angle here. The point on the unit circle is the point 0, 1. And so the y coordinate is 1, and so we get a sine value, an output value of 1 here at an angle of pi over 2. So here we've got the point pi over 2, 1. And then as we start looking at larger angles, well, the y values on this unit circle are going to start to go downwards. But they're going to be familiar angles. They're going to be the same, or they're going to be familiar outputs. They're going to be the same outputs as what we got a moment ago, right? So if I plug in an angle of And I also have to put these on the horizontal axis. So if I look at an angle of 2 pi over 3, we're again at a 30, 60, 90 triangle. We're looking at the long leg length here, so that's the square root of 3 over 2. And so that's roughly 0.85 or so. And I think that might be a reasonable place to plot that point. So this is the square root of 3 over 2. Okay, next we're going to look at 3 pi over 4. So that's another special right triangle there. That's a 45, 45, 90 triangle. It's 3 pi over 4. And so we get a y coordinate corresponding to this point of the square root of 2 over 2. And we said that's roughly 0.7. So that's about here. And then the next angle here is 5 pi over 6. That corresponds to a 30, 60, 90 triangle, but here this time we're looking again at the short leg length of 1/2. So here we're at this point, we're looking at 5 pi over 6. So this is a little crammed along the horizontal axis. Hopefully you're still able to follow along. But this is a rough sketch of this is the rough sketch of the points that we've plotted so far, corresponding to our special angles input into the sine function. And then at an angle of pi, well, we're halfway around this unit circle. Here we end up with the point -1, 0, and so we have a y value on this unit circle of 0. Should be 1/2. Here we've got 0. So here we've got the point on the graph of our sine function as pi, 0. And so I'd encourage you to pause the video and see if you can finish this graph from pi to 2 pi for all of our special angles. So 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, and so on, all the way up to 2 pi. So I'm just going to go ahead and start going through those rather quickly, assuming that you've had a chance to go through them yourself in a little bit more detail. So here the next angle would be 7 pi over 6. We'd end up with a 30, 60, 90 triangle. We look at the short leg length of 1/2, but it'd be below the x-axis on this unit circle, so it'd have a negative y value. So here we'd see this point down there. So here maybe I won't label the horizontal axis here because it gets a little crammed. But we'd be looking at 5 pi over 4 and an output value of roughly -0.7, and then at an output or an input value of 4 pi over 3, we would have an output value of roughly -0.85, so maybe down here. And then at -3 pi over 2, we would end up at the bottom point on our unit circle with a y value of -1. Then at 5 pi over 3, we would have another 30, 60, 90 triangle. We'd be looking at the long leg length, but again, this would be in the negative direction. We would still have a negative y value of roughly -0.85. At this angle out here, this 45, 45, 90 triangle would correspond to an angle of, what is that? That's 7 pi over 4. And we would have an output value of the square root of 2 over 2, so roughly 0.7, -0.7. And then we would have our last sort of special angle of 11 pi over 6. We'd end up with another 30, 60, 90 triangle, but with a short side length of -1/2. And then I guess maybe we should do one more just to really wrap this all up. At the angle of 2 pi, we'd end up with the point 1, 0, again, back to where we started. and the y-coordinate of this point at an angle of 2 pi would be 0. So here we get the point 2 pi comma 0 on the graph of f of theta is equal to sine of theta. And so here, if I sort of draw the curve that passes through all of these points, it might look something like this. So as we plug in angles past 2 pi, well, we would start going through the same values on our unit circle, right? So as I start plugging in larger and larger angles, we would start going through the same values on our unit circle, and so we'd really start repeating this graph. And so really, this is this part of the graph that we've already sketched out. It would just repeat itself as we go forward along this, and as we go back, looking at negative angles. And so here, this is just one illustration of the fact that we call this sine function here a periodic function. So a function is periodic when it completely repeats itself as we sort of increase the angles or the input values. And so here, f of theta is equal to sine of theta. This is an example of a periodic function. And how far do we have to go along our inputs before the graph starts to repeat itself? Well, this graph repeats itself every 2 pi, right? Because that's when we'll repeat our angles, not our angles, we'll start going through coterminal angles along our unit circle, and we'll start getting the same y values in the same order. And so here, this is a periodic function, and we'll usually say with a period of 2 pi. That period there is telling us how far we have to go before the function starts to repeat itself. And so maybe let's see an exact example of this, right? So here, if I plug in, for example, if I plug in 13 pi over 6, well, this is really the same as sine of, 13 pi over 6, what is that the same as? I can write that as pi over 6 plus 12 pi over 6. And I can rewrite that as sine of pi over 6 plus 2 pi, right? 12 pi over 6, that's the same as 2 pi. And so sine of pi over 6 plus 2 pi. So what I'm saying here with the fact that the sine is a periodic function with a period of 2 pi is that this is just the coterminal angle to pi over 6. And sine is going to give us the same output value at that coterminal angle. And so here, this is going to give us the same result as sine of pi over 6. Right, so sine has a period of 2 pi. It's going to repeat itself every 2 pi. And so as I plug in input values that are 2 pi more than another input value, well, they're going to give you the same result. So another thing I should mention here is that, we kind of talked about it earlier, that there's this difference between the unit circle graph and the graph of this sine function. I think, again, this is a place where it's easy to sort of get a little bit confused about because there's sort of two pictures to sort of look back and forth between. And so maybe let me ask a question here. So, one thing I can ask is whether a point is on the graph of a function or not, or on the graph of an equation or not. And so let's say I ask something like, is the point the square root of 3 over 2 comma 1/2 a point on the graph of f of theta is equal to sine of theta. So here, this first coordinate is supposed to represent the input value to our function, and the second coordinate is supposed to represent the output value to our function. And when we ask if a point is on the graph of some function, we're really asking is if I plug in this input, do we get this output to our function? And so here the question could really be seen as does sine of the square root of 3 over 2 equal 1/2? And this is not true, right? The square root of 3 over 2, this is not really one of our angles that we're familiar with plugging into our sine function. It's not going to give us 1/2 because we know what angles give us 1/2 into our sine function. Right? We've seen here that's pi over 6 gives us an angle of 1/2, or an output of 1/2 in our sine function, and 5 pi over 6 gives us an output of 1/2 of our sine function, not the square root of 3 over 2. So here what this is really saying is that no, this point is not on the graph of our sine function. Why might a person think that this point is on the graph of the sine function? Well, they might think that, this is a point on the unit circle, and this is one of those points that we use to help us evaluate our sine function. Right, this point here, the square root of 3 over 2 comma 1/2, this is a point on our unit circle, and this is a point we quite regularly use to evaluate our sine function because it's the point corresponding to the angle of pi over 6. But again, this is a point on the unit circle, not a point on the graph of our sine function. Okay, so let's go ahead and do this again, but for the cosine function. Let's graph the cosine function. Before I really dig into this, I want to talk about the variables I'm using in this equation here, y is equal to cosine of x. So when you first dealt with functions, typically you used x to represent the input of your function, and you used y to represent the output of your function. And that's really what I'm doing here, and this is what you'll see in calculus as well when you deal with these functions as well later on. You'll see something like y is equal to sine of x, or y is equal to tangent of x. Really, these x and y variables here are just there to represent the inputs and outputs of our function. When we defined sine and cosine, we talked about them representing the x and y coordinates on the unit circle. And that's true. I want you to remember that. That is true, but I want you to detach the x and y values on the unit circle from the x and y values you see in this equation. Really, the x and y values you see in this equation just represent the input to your function. X is just the input to this cosine function, and y is just the output to this cosine function. So really, that's really all I want you to think about when you see this x here. So this is just input, this is just output. Okay, so let's go ahead and sketch out the graph of this cosine function. So here we can just go through the same motions. When I plug in 0 for my angle, right, x being 0, x representing the input of our function, that's saying we've got an angle of 0 input into cosine. Well, we're looking at this point on the unit circle, 1, 0, and cosine gives us the x value on the unit circle. And so there, the output of this function is just going to be 1, right? The output of the cosine function is just the x coordinate on the unit circle, so the output is 1. And so y, the output of this function, is 1. So I know that's really confusing, but as we go through this, I think you'll start getting more of a hang of this. And so what this is saying is that an angle of 0, we get a y value of 1, an output value of 1. And so the point 0, 1 is on our graph of our cosine function. And then here at an angle of pi over 6, well, we've got the 30, 60, 90 triangle, but this time we're looking at the x coordinates on this unit circle, so this distance there, that's the square root of 3 over 2, right, for a 30, 60, 90 triangle. And we said that that's roughly 0.85 or so, so maybe here. And then at pi over 4, we're at 45, 45, 90 triangle in our picture here. Maybe I'll be consistent, I'll use blue. And we've got this distance here is what cosine is going to give us. That's going to be the square root of 2 over 2, roughly 0.7. And then, I should list that on the table, so this is the square root of 2 over 2. And then lastly, we've got pi over 3 here. So another 30, 60, 90 triangle, but with a short leg length of 1/2. And so here on our coordinate plane, an input value of pi over 3, we've got an output value of 1/2. And here, if I label my x coordinate, or my horizontal axis x for our inputs and our vertical axis y for outputs, then we're saying that when x is equal to pi over 3, when our input is equal to pi over 3, we get an output, a y value of 1/2. And then at pi over 2 on our unit circle, we're at the point 0, 1, and cosine gives us the x-coordinate on the unit circle. And so the output of this function, when we input pi over 2, is going to be 0. Okay, so let's keep going. Here, if I plug in 2 pi over 3, right, we get another 30, 60, 90 triangle, and cosine is going to give us this length of -1/2. And so that's my 2 pi over 3 is roughly here, and my output of -1/2, that's here. And so at 3 pi over 4, so we've got -1/2 here. At 3 pi over 4, we've got this x-coordinate on the unit circle. That's the square root of 2 over 2, negative the square root of 2 over 2. And so we see roughly -0.7. And then at what is this? This is 5 pi over 6. We've got an x-coordinate on the unit circle of negative the square root of 3 over 2. And so that's roughly -0.85 or so. And then the last angle I want to do together in detail is an angle of pi. So here on the other side of our unit circle, halfway across our unit circle, we're going to be at the point -1, 0, and cosine is going to give us -1 out. And so we've got some picture for this cosine function, but I definitely encourage you to pause the video now that we've done half of this picture that I really want to go through. I encourage you to pause the video and fill out the rest of the graph using your special angles from pi to 2 pi. Okay, so hopefully you've had a chance to go through that, but maybe let's go through this a little bit quicker together. So here at this angle of 7 pi over 6, we've got cosine as the x-coordinate. It's going to give us roughly -0.85. At 5 pi over 4, we're going to have an angle, or not an angle, an output of roughly -0.7. And then at 4 pi over 3, we're going to have an output, an x-coordinate of -1/2 on our unit circle. So that's going to be an output of our cosine function of -1/2. And then at 3 pi over 2, the x-coordinate on the unit circle is 0. So we're going to have the point 3 pi over 2, 0 on the graph of our cosine function. At 5 pi over 3, we're going to be back at positive x values on the unit circle. And so the output of this cosine function at 5 pi over 3 is going to be +1/2. At 7 pi over 4, we're going to have roughly 0.7. And then at 11 pi over 6, we're going to be at an output value of roughly 0.85. And then back at 2 pi, an angle of 2 pi, we're where we started. So we're going to get the same value as we got when we started. Here we're going to get the output value of 1. Right, at 2 pi, the x-coordinate on the unit circle is 1. And so if we sketch out the curve that goes through these points here, this is going to give us the rough sketch. This is a rough sketch of our graph of our cosine function. And just like before, as we go through angles past 2 pi, we're going to start repeating ourselves, right? Here, if I go pi over 6 further, I'm at 13 pi over 6, and I'm going to get the same x-coordinate, square root of 3 over 2. And so really this graph is going to repeat itself. Knowing this much of the graph is really knowing just about everything you need to know about the graph of this cosine function. It just repeats itself. So again, cosine is periodic with a period of 2 pi. So we've now graphed the sine function and the cosine function, and the results look pretty similar. Right? We have two functions that sort of oscillate back up and down as we go through the different input values. And so how can we distinguish the two? How can we do a better job of remembering the graph of cosine, remembering the graph of sine, and distinguishing the two? Well, one way that's common to think about when it comes to distinguishing these two functions is that, in some sense, the graph of the cosine function starts at a value of 1. Right? When I input 0 into my function, my cosine function, we start with an output value of 1, and this cosine function is sort of descends downwards to an output value of 0, then even further back down to an output value of 1, and then it oscillates back up. Right, and then it sort of repeats itself. But I guess really what I want you to take away here is that in some sense cosine starts at a value of 1 at its peak, and then sort of goes down to a value and back up. And if we look at the graph of our sine function, so here if we look at the graph of our sine function, we see that the sine function starts, when we look at the vertical axis, it starts at an output value of 0, sort of in the middle of the function, not at a peak or at its lowest point, but right through the middle of its output values. And then it heads upwards towards a peak, and then back downwards, and then continues to oscillate. So in some sense, the sine function starts at an output value of 0 in the middle of our function. The outputs of our function goes up and down, and then the cosine function, it starts at a peak, it starts at an output value of 1, and then goes down and then back up and then goes through the typical oscillations. And so if we look at these two different graphs here, I think I've kind of messed up this problem by my use of colors, but here if we look at these two different graphs, how can you tell which one's the graph of a sine function, which one's the graph of the cosine function? Well, we can see that this graph here on the bottom sort of has its vertical intercept at an output value of 0, and then it sort of goes upwards and then back downwards and sort of goes through the typical oscillation of these sine functions and cosine functions. And then the cosine function here, well, here it starts at its peak at an output value of 1 and then sort of oscillates back and forth. So here this is the equation y is equal to cosine of x, and then maybe I'll kind of label the bottom one in the same way. This is y is equal to sine of x. So in the past we talked about the domain and the range of all of our different trigonometric functions. And here, now that we've graphed the functions y is equal to cosine of x and y is equal to sine of x, this gives another way for us to actually quickly identify what the domain and range of these functions are. And so the domain is a set of all input values for our functions. And when we look at a graph of a function, we can sort of see that by looking at how far left the graph goes and how far right the graph goes, and if there's any spaces in between that are cut out. But we can see here that the domain, how far left these two graphs go, and how far right these two graphs go, well, they really go out left and out right. They go on and on forever in both directions. And so here the domain of both of these functions may go from negative infinity to positive infinity, which is what we said before. Now what about the range of these functions? Well, the range is a set of all outputs of our function, right? So how high up our graph goes and how low our graph goes. And so here we can see that our function, our sine function, actually our cosine function as well, well, they're going to vary their output values between negative 1 and 1, right? They're never going to exceed negative 1, they're never going to go below negative 1, and they're never going to go above positive 1. And so here the range, and this is the case for the cosine function as well, goes from negative 1 to 1, and we're including negative 1 and 1 because we do get output values of negative 1 and 1.